Physics Part 420. Well, we've got normally on the boundary the parallel beams ultrasound incident, and they are A, air and soft tissue, B, muscle and bone that has a specific acoustic impedance. Now it's your turn. Using data from the table, A suggests why, although the speed of the ultrasound in blood and muscle is approximately the same, the specific acoustic impedance is different. B. Calculate the intensity reflection coefficient for a parallel beam of ultrasound incident normally on the boundary between the fat and muscle. It can be seen that the intensity reflection coefficient for a boundary between air and soft tissue is approximately equal to unity. This means that when ultrasound is incident on the body, very little is transmitted into the body. In order that ultrasound may be transmitted into the body and also that the ultrasound may return to the transducer, it is important that there is no air between the transducer and the skin soft tissue. This is achieved by means of water-based jelly. This jelly has a specific acoustic impedance of approximately 1.5 into 10 to the power raised to 6 kilogram per meter per second. Once the ultrasound wave is within the medium, the intensity of the wave will be reduced by an absorption of the energy as it passes through the medium. The medium is heated. In fact, the heating effect produced by ultrasound of appropriate frequencies is used in physiotherapy to assist recovery from sprains and similar injuries. For a parallel beam, this absorption is approximately exponential. As with X rays, for such a beam ultrasound incident normally on a medium of thickness, and the transmitted intensity is related to the incident intensity by such an expression. Well, K is a constant. The coefficient of K depends not only on the medium itself but also on the frequency of the ultrasound. So values of the linear absorption of coefficient are shown in the table as provided here. Well, medium air has got the linear absorption coefficient 1.2. For medium bone, it is 0.13. For medium muscle, it is 0.23. For medium water, it is 0.0002. We've got an example for you. A parallel beam of the ultrasound is incident on the surface of a muscle, reflected at the surface of the bone, and returns through the muscles to its surface. Using the data from the table, calculate the fraction of the incident intensity that arrives back at the surface of the muscle. Now it's your turn. A parallel beam of the ultrasound passes through the thickness of 4.0 centimeter of muscle. It is then incident normally on a bone having a specific acoustic impedance of 6.4 into 10 spot raised to 6 kilogram per meter per second. The bone is 1.5 centimeter thick. Using data from the table, calculate the fraction of the incident intensity that is transmitted through the muscle and bone. Obtaining diagnostic information using ultrasound. The ultrasound transducer is placed on the skin with water-based jelly excluding any air between the transducer and the skin. Short pulses of ultrasound are transmitted into the body where they are partly reflected and partly transmitted at the boundaries between media in the body, such as fat muscles, fat muscles, and muscle bone. The reflected pulses return to the transducer where they are detected and converted into voltage pulses. Voltage pulses. These voltage pulses can be amplified and processed by electronic circuits such that the output of the circuits may be displayed on a screen, as in, for example, a cathode ray oscilloscope. Well, we'll talk more about the ultrasound and its features. And of course, we'll talk about the diagnostic information that we get by ultrasound in our next video, the forthcoming videos tomorrow. That's all for the night. Bye bye. Take care. See you tomorrow. Talk to you tomorrow. That's all for the day.